These are our first notes for this week. We are now in volume 2 of our math books. This is chapter 13, section 1 on page 841. Notes 23 on probability. So this whole, we're starting unit 6. So this whole unit is based about probability and, how likely different events are to occur. So the essential question here is, how do I calculate experimental and theoretical probability? Pause it whenever you need to write this down. Maybe you want to pause it and then unpause and listen as I explain it. So here's some vocabulary words. Outcome. So you'll be hearing all these different words: outcome, event, sample space, probability. And if you forget what it means, look back here. So outcome, a possible result of a situation or experiment. Event, a single outcome or group of outcomes. Sample space, set of all possible outcomes. Probability, measure of the likelihood that an event will occur between 0 and 1. So probability of an event would equal the number of favorable outcomes divided by or over the number of possible outcomes. And this is really important. Let me slide it up just a little. That probability can be written as a ratio or a fraction with one number on the top, one on the bottom. You can also then divide that and get a decimal. From that decimal, you can multiply by 100 and get the percent. So when we first set it up, the way to calculate it, probability of an event would be one number over another, the number of favorable outcomes over the number of possible outcomes. But then when you write your final answer, it might be a fraction and you have to reduce it. So like if you had 2 over 6, it would reduce to 1/3, 1 over 3. Or you might be asked to give it as a decimal. So then you would actually divide the top number divided by the bottom. Or as a percentage, then you would just multiply whatever that decimal is by 100. All right, here is one more thing about probability. This is showing what that value would actually mean. So thinking of our value as a decimal, 0.5 is in the middle, and 0 is at the left end, and 1 is at the right end, kind of like a number line. So you can imagine it would be 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. So think of it like a number line. If you get a probability of 0 or really close to 0, it's impossible or very unlikely to occur. If you get a probability close to 1, or if it is 1, or if it's like 0.9 or something like that, it is certain. It's very, very likely to happen. If you're exactly halfway, it's equally likely to occur or not to occur. The closer you are to 0, the less likely it is to occur. The closer you are to 1, the more likely it is to occur. So again, it's the more likely to occurs are like 0.6, 0.7, 0.8, 0.9, and 1. Less likely to occur, 0.4, 0.3, 0.2, 0.1, and 0. Okay, so again, pause it if you need to. I'm going to go ahead and slide this up. And we're going to go over experimental probability. So again, pause if you need to. So this starts on page 842. Let me see how I can move this. Ooh, that got crooked. Okay, so pause it if you need to again, whenever you might need to if I start going too fast. So this says, when there is an actual experiment, you can find experimental probability based on the results of the experiment. So for example, if you have a coin and it has two sides, heads and tails, in theory, they are equally as likely to occur. You know, if you get a 1/2 chance of getting the heads or 1/2 chance of getting the tails. If you do an actual experiment, if you maybe flip the coin 10 times, you may not get exactly half the time heads and tails. You might get 3 of the times heads and 7 of the times tails. So experimental probability is when you actually go through and do an experiment, or you actually have real results. So it's based on results of an experiment. So for experimental probability, this is how we're going to calculate it. Probability of an event, it's very similar to what we had up above, but it's the number of times an event actually occurs divided by the number of times the experiment is done. And then here's our example. So again, you might need to pause, write this down. I'm going to start reading it just in case. So like if you pause it and then you're waiting. So a classroom of students were surveyed, which means they were asked this question. And out of 36 students in this one classroom, 12 of them walked to school. So the first question is, what is the experimental probability that a randomly selected student in that class walks to school? So we're going to go ahead and set that up. Okay. So probability, the event here is that they walk to school. So we have the fraction, a number on top and a number on the bottom. So on the top, I need the number of students who do walk to school. So 12 students walk to school. So 12 is on the top. And then on the bottom is the number of times the experiment is done. That doesn't really make sense here, but it's like the number of possibilities, or in this case, it's just the total number of students. So it's 36. So it's the number that walk over the total number. So like I was saying above, your percent can be written as a fraction or ratio, but it has to be reduced, or a decimal, or a percentage. So I just wanted to show you guys all three, at least for this example. So 12 over 36, I can divide by 12 to reduce the fraction. So divide the top and bottom by 12. So then I would get P, probability of walks, is 1 over 36 divided by 12 is 3. Or in my calculator, I can divide and get the decimal. So 1 divided by 3 is 0.33 repeating. Or as a percentage, I would multiply that times 100, which is basically just moving the decimal place 2 times to the right. So, or 33%. So those are the 3 different ways you could write it. Okay. So what we're going to do on the next part is, using this experimental probability, we're going to expand it to the whole school. So predict about how many of the 2,624 students at school walk to school. So probability, we're still saying walk. We already have the percentage of the one classroom, and we're going to expand it kind of based on that pattern to the whole school. So I would have to do my 0.33 or 1/3, whichever one you prefer, but I think we mostly prefer decimals. 0.33 repeating, and then multiply that times the total number of the students in school, 2,624. And I picked this problem because you'll have one like this in your Math Excel. So just so you know, this is how you do it. First, find the probability of walking students in the classroom, and then multiply that probability. I prefer to pick the decimal, multiply that decimal by the total number. And so we're going to get it right now. 0.33. Remember that it did repeat, so I want to just do a bunch of 3s just to get a more accurate value, times 2,624. Now remember, we're calculating people. There's no 0.66 of a person, so I would either round up or down to the nearest student. I would go ahead and round up, since 0.6 does round up. So I'm going to now do approximately 875 students. Actually, that's not probability. It's not probability, it's just the number of students who walk. So approximately 875 students walk to school. All right, so now we're going to go on to, this was based on an experiment based on like real actual data, real numbers. Now we're going to move on to theoretical probability. So first, let's write this down. Let me tell you what page that's on too. I forgot to write the page number. This is on page 843 in the book. And remember, if you don't have the second volume of the book with you, the book is available online at Pearson. Just instead of clicking Math Excel, you can click on the other thing, which is the online textbook. So Notes 23 continued, page 843 is theoretical probability. It describes the likelihood of an event based on mathematical reasoning. So based on theory, based on kind of like common sense, if that makes sense. All right, so to find the theoretical probability, it's the same as before. Probability of an event equals the number of favorable outcomes divided by the number of possible outcomes. So, but it's not based on an experiment. This is based on, like, if you have a dice and it has 6 sides and they're numbered 1, 2, 3, 4, 5, 6, each side is, in theory, as likely to come up as any of the other sides. So, like in theory, I could say, what's the probability of rolling a 2? And there's one side that has a 2, so 1 over 6. If you did an actual experiment, it could be different. You could get that rolling a 2 could come up more likely than one of the other numbers. Anyways, here's the example for theoretical probability. Go ahead and copy it down and we'll get started. If you need to pause, you can pause. So it says, a bag contains letter tiles that spell the word California. So what this makes me think of is Scrabble. If you've ever played Scrabble, there's a bag that has a bunch of tile letters, little, let me just draw it for you so that you can see. It's like that. And so since it spells California, you know, one of the letters would be a C, one would be an A. Actually, 2 would be A's. So you'd have 2 tiles that are an A, one that's an L, 2 that are I's, a F, a O, a R, and an N. So there's CALIFORNIA. I think that's 10. There should be 10 letters. So some have more than one. There could be 2 A's, 2 I's. So anyways, find the theoretical probability for drawing one tile at random for each of the following. So imagine just this one. You reach in the bag. What's the probability of getting a C? And then you would put that tile back, whatever tile you got. What's the probability of getting an I? Here, it's a little different. What's the probability of getting a vowel? So think A, E, I, O, U. How many of those tiles are in there out of the total? And then one more thing I wanted to go over with you guys is probability of a complement, which is on page 844. So I'll talk about that when we get there. Okay, so copy that down, and we're going to go ahead and get started. Pause it if you're not ready yet. And again, we're going to be thinking of the number of favorable outcomes divided by the number of possible outcomes. Okay, so probability of getting a C. So I'm looking at California. I need to see the number of favorable outcomes is how many C's are there? There's only one. Out of the total number of letters, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, if I can reduce that fraction, I would want to. Or in your homework, it might ask you to write it as a decimal. I can't remember what it says to round to, so just be careful at what place it says to round to. So I would do 1 divided by 10 to get the decimal. It's 0.1. And so looking at that, thinking about what we wrote on the other side, it's not very likely that you would get a C. It's 0.1. It's very close to 0. So let's see if any of the other ones are more likely than getting a C. All right, so probability of getting an I tile. Drawing one tile means picking one tile out of the bag. So I would count how many I's are there. There's 1, 2. Those are the favorable outcomes out of the total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I do need to reduce that, so I divide the top and bottom by 2, and it's 1/5. Or I want to just show you guys again how to write this as a decimal. Just so you know, you could do 2 divided by 10, and that still gives you the same answer. Or 1 divided by 5, it's still 0.2. There's not a lot of room to write that. Okay, 0.2. All right, so that one is actually twice as likely. You're twice as likely to pick an I rather than a C. But 0.2, when you're thinking about how likely something is to happen, it's still in the less likely area. It's not very likely. All right, let's count up how many vowels there are for the next one. Probability of a vowel. So A-E-I-O-U. I see 1, 2, 3, 4, 5. 5 out of 10, which is 1/2. Which, if you need to use a calculator, use a calculator, but that is 0.5. So thinking about that, it is equally likely to occur as not to occur, 0.5. So the least likely thing is to pick a C, then an I, and an I would have the same likelihood as an A, the same probability, because there's two A's and there's two I's, but there's half, like a 50% chance that you could pick a vowel. Or a consonant, there's a P, R, B, L, T. Okay, so now real quick, the part I was saying about the complements. So in the book, I'll just show you guys my book real quick. You don't need to write this, but I thought we should talk about this. The complement of an event consists of all the possible outcomes in the sample space that are not part of the event. So for example, if you roll a standard number cube, the probability of rolling a number less than 3 is P rolling less than 3, which is 1 and 2, so 2/6 or 1/3. The probability of not rolling a number less than 3 is basically, so since that's 2 out of 6, it would be 4 out of 6, or 2/3 when you reduce it. So when you add up the probability of an event and the probability of its complement, they add up to 1. So that's just one thing I kind of wanted you guys to see. The probability of an event and the probability of the event not happening would be 1. So if we kind of just think about that real quick with what I just went over, we could have the probability of getting a C tile, which is 1 out of 10. The complement would be, you don't need to write this down, but just so you guys can see, it would be the probability of not C. How many letters are not C? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 10. So do you see how it's 1/10 and 9/10, and together they add up to 1? That's what the complement is. It's saying not in front. So I basically actually kind of showed you what to do here for number 4. So the probability of not getting an I, still looking at California, there's still 10 letters to pick from. How many of them are not an I? Well, you could easily count them, and you would count 8. But I could see really quick over here, the probability of an I was 2. So I would know that there's 8 other letters besides I. And then you have to reduce it still. Divide the top and bottom by 2, so 4/5. Now that's pretty likely to occur. It's pretty likely that you would get not an I letter. Oh yeah, I know that's 0.8 or 0.8. Again, you should know how to find the answer either as a reduced fraction or a decimal. And if it does say as a percentage, that would be 80%, just so you guys know. All right, the probability that this is not a vowel letter is still out of 10 letters. We're thinking of California. I already found the probability of a vowel. It was 5 out of 10. So if you subtract, that would leave another 5. There's C. I'm going to count. That's 1, the L, the F, the R, the N. Okay, that's 5. So that's 5/10, or 1/2, or 0.5, or 50%. So you're equally as likely to pick a vowel or not a vowel or a consonant. Okay, so that's what a complement is. It's basically the opposite of the one that is like probability of an I or probability of not an I, probability of a vowel or probability of not a vowel. Okay, so anyways, that is it for the notes. We do have a Math Excel assignment, so make sure you do that in practice. And make sure you guys still do your 3 questions on the left and a summary, 3-sentence summary at the end.